The purpose of this video is to walk you through an example with sample proportions following the state plan do conclude 4-step process that we will be using throughout this chapter on sampling distributions. It is highly recommended that you have read section 9.1 before watching this video, otherwise things may not make sense to you. The second thing that I would advise is that you download the template from the website, which is a graphic organizer for state plan do conclude, to help walk you through these steps. If you haven't done that, please go ahead and do so now. Pause the video and then unpause once you have these items completed. We're going to work with example 919 from page 588 in your textbook. I'll give you a couple of seconds to read over this. I really want to focus on parts A through C of this question, and that will help us complete the state plan do conclude. We're focused on the question of finding the probability that 67% or fewer respondents would respond that they actually drink the cereal milk, and whether or not we should be doubtful about the results of such a poll. So let's begin with state. We want to find the probability that a given poll gives us a sample result where 67% or fewer of the respondents say that they drink the cereal milk. In symbols, that is the probability that p hat is less than or equal to 0.67. In the planning phase, we want to make sure that we verify all conditions that must be in place in order for our results to be valid. These conditions will be verified over and over again throughout the next 4 or 5 weeks. So the first one is that we have some form of randomness, either in the selection process of our sample or in the assignment of treatments and experiments. The other is that we have to have some form of independence in sampling, and there are ways around that, which we'll talk about. The other thing that we have to have is some idea that normal approximations will be valid, and so we just call that the normality condition. So let's begin to look at how we verify these. Let's begin with randomness. Randomness is pretty easy to verify. You either are told the information in the scenario or you are not. In our case, we are told that this poll asked a random sample of 1,012 U.S. adults, and so we want to make sure that we make that clear. So we have a random sample of 1,012 U.S. adults. It's as simple as that. That information is given to us, nothing that we really have to do. The next one is independence, and this has more to do with making sure we can use the formula given for the standard deviation. Standard deviation assumes that our proportion remains constant throughout the sampling distribution building process. However, when we sample without replacement, which causes a problem because sampling out without replacement leads to dependence in sampling. And so what we need to make sure of is that we don't take a population size, that we don't take a sample that's so big of a piece of our population that we invalidate the formula that we're using for standard deviation. So what we say, we use this thing that we call the 10% rule. And the 10% rule says that your population size, capital N, has to be at least 10 times as large as your sample size, which in turn means that your sample size can be no bigger than 10% of your population size. When this rule is met, then the formula that we use for standard deviation of the sampling distribution of the p-hats becomes perfectly valid. And so this formula is valid as long as the 10% rule is in effect. So we asked 1,012 U.S. adults. So the question you must ask yourself is whether or not it's reasonable to believe that we have more than 10 times that number of U.S. adults in the entire population. And I think we'll agree that the answer to that question is yes. And so this has been validated in terms of our standard deviation formula. The last condition we want to verify is that we can use the normal distribution. And this should be very familiar to you from the work we just finished in Chapter 8 with the binomial. This is a binomial situation. And it's binomial because as we ask this question, either a respondent will say yes, they drink the cereal milk, or no, they do not. We're asking different people, so one person's response is not influenced by another person's response since they are different. And the probability of success, which is 70%, is remaining the same because that's the percent that we suspect actually exists in the population. So that's not changing at all. And we are interested in the number of respondents who would respond yes. So this is a binomial situation. So you should recall that in order to approximate the binomial, we need at least 10 successes and at least 10 failures to exist. Let me clean that up a little bit. Here we go. So I need at least 10 successes and 10 failures. And so we can verify whether or not that's true. We have 1,012 in our sample. And so I would want to multiply that by 0.7 for success to count the number of expected successes. And I would want to multiply it by 0.3 to count the expected number of failures. So we should find that we have 708.4 expected successes and 303.6 expected failures. Please don't worry about the fact that these are decimals. It does not matter at all. The fact is that they are both greater than 10. Okay, so since we have at least 10 people who we would expect to say yes, they drink the cereal milk, and at least 10 who we expect to say they do not drink the cereal milk, we can assume that p hat follows a normal model. And so just something about this p hat following a normal model. What we're assuming is that we are taking an infinite number of samples, and we are asking this question over and over again. And as we are recording those p hats, they are forming their own distribution. So these are all of the p hats, and ideally this would follow a normal model with a mean and a standard deviation of its own. So let's talk about what the mean and standard deviations would be. So from what we just discussed, we know that p hat follows a normal model. And now that we know what that shape is, of course we want to talk about the center and spread because that's what normal distribution is defined based upon. Now, the good news is that you don't have to think much about the center. Whenever we create this normal distribution that is the sampling distribution, the mean of the sampling distribution, and we represent that with mu p hat, is equal to the population proportion. And remember from before, the population proportion is 0.7. And that has to do with unbiased estimators. We'll talk about that in class tomorrow. Now, the standard deviation, I gave you the formula for that earlier. We take the square root of p times 1 minus p all over n. And that is related to the binomial as well. If you're interested in y, see me individually, and we can talk about that. So we have a mean of 0.7. And then solving for standard deviation, we would take the square root of 0.7 times 0.3. Divide that by 1,012, and we get a standard deviation of 0.0144. And that ends the planning phase. So next we'll go to the do, and then finally conclude phase. In the do phase, we actually want to perform the calculations that help us answer the question of what's the probability that we'll find a sample whose proportion of respondents who say they drink the cereal milk is less than or equal to 0.67. Recall that a z-score takes an observed value, for us that's p hat, subtracts its mean, for us that's mu p hat, divides by its standard deviation, for us that's sigma p hat. So to answer this question of the probability that p hat is no more than 0.67, that's like taking that z-score and saying, okay, the probability that z is less than 0.67 minus 0.7 divided by 0.0144, or the probability that z is going to be less than or equal to negative 2.08. if you look on your table, you should find that this probability is about 0.0188. And so now the question of whether or not this is unusual. And this is a line of thinking that we have to follow. Remember, the assumption is that 70% of U.S. adults actually drink the milk. We took a sample of 1,012, and this was a random sample. So assuming randomness and chance are at work, only 67% said they drink the milk. Obviously, there's a difference between this 0.7 and this 0.67. But is it a significant difference? Is it a statistically significant difference? If 70% is the actual population proportion, then we expect 0.67 to be relatively close to it. But we find that in only 1.88% of all samples that we take of size 1012 would result in such a sample proportion. And so as a result, yes, we do have reason to be concerned. And so as we conclude, that's what we will state. This result is rather unusual. Do over. And again, the reason why is only 1.88% of all samples would result, or I should say would have results this far away from the mean. And we will work more on that interpretation. You'll be using it over and over again from now until the end of the semester. But I just wanted to walk through an example with you. Make sure that you have recorded the information. If you need to watch this again, watch it. If you need to pause and rewind, you can do that too. It's a video. There's nothing stopping you from doing that. So make sure that you're ready for class tomorrow. We'll be working with Fathom, and these ideas will hopefully be clarified for you. And I'll see you then.